Hello everyone. In this video, we're going to present our work called CompGS, a smaller and faster Gaussian splatting with vector quantization. 3D Gaussian splatting, or 3DGS, proposes to use 3D Gaussians as a new representation for radiance field that provides real-time photorealistic rendering quality even for a complex scene. To render a given scene, 3DGS starts with a set of cameras and a point cloud provided by a structure from motion during camera calibration. Then, they optimize a set of 3D Gaussians to represent that scene. Each Gaussian has its own attributes to model scene's geometry and appearance. Finally, they render transparent Gaussians with their fast, tile-based renderer and backpropagate the gradients to their attributes. Once trained, the scene is composed of millions of Gaussians. Since each point and its attributes are stored independently, significant number of Gaussians in 3DGS representation introduces a significant storage cost. For instance, 3DGS requires 1 GB to render 360 scene of a bike that inhibits its scalability. This drawback of 3DGS inspired us to come up with our method, CompGS, to compress 3DGS by both reducing the total number of Gaussians in a scene and reducing the storage requirement for each Gaussian. It compresses 3DGS by 40 to 50 times and speeds up rendering time by 2 to 3 times with little drop in quality of rendered images. Our main intuition is that several Gaussians may share some of their parameters, for example, covariance matrix. So we vector quantize parameters while optimizing them using simple k-means. Now we only need to store a small codebook of cluster centers along with the index of the code for each Gaussian. This can result in a huge reduction in the storage and potentially the memory footprint at the rendering time. Here is how our method CompGS works. Considering each Gaussian as a vector, we perform k-means clustering to represent n Gaussians in the model with k cluster centers. Each Gaussian is then replaced by its corresponding code for rendering and loss calculation. The gradients with respect to centers are copied to all the elements in the corresponding cluster, and the non-quantized versions of the parameters are updated. Only the codebook and code assignments for each Gaussian are stored and used for inference. To further reduce the storage and inference time, we regularize opacity in the loss function to encourage fully transparent Gaussians. So the final loss becomes summation of original loss of 3DGS, and lambda controls the sparsity of opacity. Gaussians with opacity smaller than a threshold are removed. These results show the comparison between CompGS and other state-of-the-art novel view synthesis methods. CompGS with codebook of size 32K maintains the performance advantages of 3DGS, while on average being more than 40 times smaller and 2 times faster at rendering time. CompGS 32K 8 bits is the post-training bit quantized version of CompGS. It further increases the average compression ratio to nearly 65 times with a small drop in rendering quality. Here are the visualized results of CompGS in the top row compared with 3DGS in the bottom row. There are no visually apparent differences between the two methods. CompGS captures high-frequency components and finer details like the spokes of the bike, as well as 3DGS. In addition to the typical 3 datasets comprising 13 scenes, we show results on 2 large-scale datasets. We repurposed 200 scenes from the ARKit video understanding dataset for the novel view synthesis task. DL3DV NVS benchmark consists of 140 scenes sampled from the larger DL3DV 10K dataset. Similar to the previous results, CompGS achieves a high level of compression with a small drop in quality. Thanks so much for watching our video. Please refer to the paper for more details.